So just a quick example of how TDoA techniques can be used even in some of the most challenging conditions, looking for transmitters with very narrow beam width. So often with TDoA, we're assuming that we're looking for a signal which is being transmitted out, and it's illuminating all of our receivers at the same time. So TDoA is synchronously looking, hunting for signal type, correlating the data, and then deriving back to the location. But what if let's just run a little simulation here. We're down the south coast of the UK. I've got 4 of our receivers, 1, 2, 3, 4. And here I have the spectrum, and you can see, I can see the signal popping up, pink, gray, purple, green. And then what happens is the signal is sweeping back, green, pink, gray, and purple. So let's just quickly reveal what the transmitter looks like in this case. Something, of course, you can't really do in real life. But here I have the transmitter, which is just inside the international waters. And we've got a very, very pencil thin beam. It's 5 degrees, minus 60 dBm side load level. So very precise signal. I can even turn this into a pulsed transmission signal as well if I wanted to do that. But as you can see, with this network of receivers, we're not illuminating all 4 of the receivers at the same time. Therefore, the synchronous TDoA measurement is really no good to us. So we're pretty well defeated. Well, don't despair. We do have solutions here. What we do is just a little bit of technical jiggery pokery. Just reopen that again. And what we do actually is we're having our receivers, rather than one network of receivers all performing the same synchronous measurement, what I'm doing is I'm now splitting the 2 receivers here and the 2 receivers here into 2 separate networks, which will be running their own spectrum and running their own TDoA. Now, the clever trick is in the TDoA. In processing, what we're doing is we're not looking for 3 or more nodes, we're actually looking for 2. So instead of providing a TDoA geolocation, 2 dimensions, what we'll get now is we'll get an isochrone, or we'll get a bar which shows the potential locations of the signal relative to the 2 receivers. So it's almost like a signal vector, if you like. The other clever thing we're going to be doing is averaging the heat map data over time. So actually collecting and storing and averaging the data. When we get a hit, we're actually going to be keeping the display on the screen permanently. So we're just holding, or the quench is set to 0. So let's run that. And with the spectrum, we can also show you a little bit of what's going on. So sorry, the spectrum's not showing for this guy. Let me just show you there. Doop, doop. There you go, both spectrum missions coming. So you can see what's happening here is the beam is sweeping around. It's going to illuminate the gray one next. Oh, sorry, the blue and the gray on this side. So it's illuminating those guys. It's sweeping around, swept through those 2. And what's happening is the TDoA engines are drawing the isochrone. In other words, the position or potential position. Oops, sorry, I've dragged that up. Of the transmitter, and then storing the data on the screen. Now, the interesting thing, of course, is where those 2 isochrones cross each other. This is now the location of our transmitter. You get a little bit of intermittent things as the signal to noise isn't great, or the averaging hasn't quite worked out. We could go back and play with the averaging screen here. But just with a little bit of patience and let these sweeps accumulate up, what you'll see is where those isochrones are actually crossing each other. This is actually the location. Sharp-eyed people will notice that the location here is actually changing a little bit with time, and that's simply because in my transmitter, what I have the transmitter doing, click, click, is actually the transmitter following a flight path in and out here. So it's actually moving up and down. Let me just show you where he is. Oh, perfect. And then the beam that's coming out from him and sweeping around and illuminating the various devices. So with appropriate geometry and a clever bit of technical jiggery pokery, we're able to still, even just with 4 omnidirectional receivers, 2 sets of 2, be able to perform this isochrone. Overlaying the isochrones, here we go, is actually giving us the geolocation of a narrow beamed transmitter on a flying object here, an aircraft in this case. So it's kind of a cool way of being able to do this in a very simple and very cost-effective methodology without having to resort to the much more expensive AOA systems. Interesting technology from CRFS. Thanks.